Hello everybody, my name is Thomas Trauch and today we are going to continue with Proposition 18 of Gottfried Wilhelm Leibniz's work on the arithmetic quadrature of the circle, ellipse and hyperbola. And in this proposition, Leibniz is proving that certain areas, like as depicted here as zone 1, which is a kind of a segment of a parabola in this case, and a zone 2, which is bound by the abscissas, the section of the curve we are looking at, and the axis is actually equal to the proportion of the involved dignity powers. It's like omega as the power of the v dignity and e as the power of the y dignity. And this proof bears some relevance because it is actually an expression of the acting principle as a relationship between these two areas. And when you look at how these two areas are related to each other in terms of the construction, you can already see some going into the direction of dx and the dy. The dx, for instance, possibly being a distance between the g1 and the g2 point, and the dy being the b1 and the b2 point. And if they become infinitesimally small, such that the quantities disappear, but the principle which they are related to, namely their proportionality, will remain even if they are infinitesimally small. And this is what Leibniz's point was about. And people today make the mistake of kind of associating quantities or trying to associate quantities with the infinitesimal, which is not possible because you're operating in the realm of infinity. And in the infinitesimally small, what is happening there is that the term of quantity is not relevant, it vanishes, but what remains is the principle between, like in this case, these two areas. It will remain even when you're dealing with infinitesimally small entities. And for the proof of this particular relationship, Leibniz did the following, and we're going to go through these steps now. The proof is actually done again via an intermediary. And like in many of the propositions before, the sector area becomes here the intermediary again. And from Proposition 17, we know that 2 times the sector is actually equal to the zone multiplied by the proportion of the dignity powers, so omega minus e, divided by omega. So this we already found out. And this we are going to use now as a building block for the purpose of proving this relationship up here. In the next step, what Leibniz did is to conjugate the parabola. So conjugating a curve in this, or in terms of this analytical expression, means that you just exchange the v and the y dignities in this case for each other. So where you had the y dignity before, you now have it substitute with the v dignity, and vice versa, the v dignity with the y dignity. This is a conjugation, and it's actually not representing nothing else than a mirroring around the axis of the function y equals v, which is kind of a diagonal of going down in this quadrant. And this is used for a particular purpose, because in order to make the relationship knowable between the blue area, the zone 1, and the red area, the zone 2, you have to kind of make the same principle that is existent between the sector area and the zone 1 area also valid for the some kind of sector area and the zone 2 area. And this is why he conjugated it, because now when you also conjugate the points C1 and C2, 2 and place them on the conjugated parabola, you can create the absolutely identical areas also on the conjugated parabola, such that we have for zone 1, you have a conjugated zone 1 dash on the conjugated parabola. For zone 2, there exists a zone 2 dash, the conjugated version of it, and also the sector has a conjugated version. And now it is clear that the sector, which stands in this relationship up here with the zone 1, the same type of relationship must actually be valid like between the sector dash and the zone 2 dash, because it's also a sector which sort of stands in a relationship to a segment of a curve, just that the curve is not the parabola anymore but the conjugated parabola. And because it can be safely assumed that the areas by the operation of the conjugate are identical, in area and even also in shape, we can actually use these conjugated areas to prove exactly this, because we know that the zone 2 dash is exactly the same size as zone 2 area. All right, so and there we go. So we know that 2 times the sector dash, so the conjugated sector area, is equal to the zone 2 times omega minus e divided by e, because zone 2 can easily be substituted with the zone 2 dash, and that's standing in the same relationship with the sector dash as the sector is to zone 1. So you have this expression, and you notice that in terms of the dignity powers, you don't have a ratio anymore like omega minus e divided by omega. Here you have omega minus e divided by e, because due to the conjugation and using the sector dash, the e dignity becomes the y dignity, sort of. And because we know this now, and we know that 2 times the sector can actually be substituted with the sector, because they are also identical, you can make up the next expression being the zone 1 multiplied by omega minus e divided by omega is equal to the zone 2 times omega minus e divided by e. Zone 2 or zone 2 dash, doesn't matter, they are the same, they are identical. And that's why you can do this. And when you now resolve this expression, because some things can be cancelled out, and the omega minus e is actually disappearing because it cancels itself out in this expression, you get the expression that we actually wanted to prove, like zone 1 divided by zone 2 is equal to omega divided by e. And this is what was to be proven, and this is a very simple relationship, but it bears so much relevance because the parabola as an analytic expression and as an acting principle, which is like expressed graphically or geometrically in this curve, is inherent in its dignity powers. That means that the areas like the zone 1 and the zone 2 are proportional to the dignity powers based on this proportion, like the v dignity divided by the y dignity. And this is the actual basis for this notation of the calculus, especially with polynomial functions, where you have this mode of operation that Leibniz introduced, which made it so easy and so fast to quadrate figures below curves, of quadrate curves, or these kind of things. This operation made it so fast to get results, and made it like as easy, such that a child actually could do it. And this was something absolutely new, and it changed the whole phase of geometry and mathematics, if you will. But this is not only true for the parabola, because the ratio of these dignity powers can express an expression of any type of curve, like not only the parabola, but the whole set of paraboloids, and also for the hyperbola and for hyperboloids. And this is the next step where we would like to demonstrate this very same principle. So you have a hyperbola, and you basically draw out the very same figures. It's just that it may be a little more dense and confused in terms of the hyperbola, because there's not so much space here to draw these areas, but we're gonna get along. So we want to prove the same expression, zone 1 divided by zone 2 is equal to the v dignity omega power divided by e as a power of the y dignity. And the conjugated term then vice versa. So e becomes the v dignity and omega the y dignity. The same principle holds true for the hyperbola, that we learned that also in Proposition 17, that 2 times the sector again is the zone 1 multiplied with omega plus e divided by omega as a dignity power ratio. And you notice that this time we don't have omega minus e, but omega plus e. And this was specific to the hyperboloids. And we already proved this in Proposition 17. And here again, we're going to use it as a building block for the next proof for the hyperbola, to prove this expression here up here. So now you basically follow the same principle as we already did in the parabola. So you have a zone 1 originally, but you also have a zone 1 dash as a conjugated area on this curve. So when you conjugate the hyperbola, because it's actually symmetric to the line of y equals v, and when you mirror the parabola, you actually get the very same curve. So that is why the conjugate areas actually are bordering the very same hyperbola itself, because the conjugated hyperbola is exactly the same as the original hyperbola. So you have zone 1 dash, zone 2 dash, and sector dash. And you apply the same principle now to prove this relationship up here, namely making sure that 2 times the sector is actually equal to the zone 2 multiplied by omega plus e divided by e. And then you substitute basically sector dash for sector, and it means that you can directly compare those. So now you have the expression from here, zone 1 multiplied by omega plus e divided by omega as the dignity powers is equal to this expression down here, zone 2 multiplied by omega plus e divided by e. And this again is possible because we know that when we build the conjugated areas of these original areas that are basically produced by the C1 and the C2 point, and when we conjugate these points on the hyperbola, we get exactly the same size of areas in terms of the segment, the zone 1 and the sector. So they're identical. This can be assumed without any problems. So also for the hyperbola, when you resolve this expression up here, you end up with the very same expression as with the parabola, that's the zone 1 divided by zone 2 equals omega divided by e. And this was to be proven. And yes, it is to be understood that this relationship, this proportionality of these areas is actually the principle of the using of the infinitesimal, also in terms of this notation which Leibniz created for the operations of differentiating and integrating certain polynomial functions, or actually all polynomial functions with a few exceptions. And yes, the principle of the infinitesimal is one aspect where you say that when you go into the realm of infinity, meaning that you make these distances between these points infinitely small, it will still be clear that the areas that are produced by these constructions, which also become infinitesimally small, will still be in the same type of relationship to each other, even if the infinitesimally small. So while the quantities disappear in the infinitesimally small, the principle remains. And that is the actual important point, because this is reducing it to the acting principle of the curve, the acting principle of the hyperbola, or the acting principle of the parabola. And this acting principle is inherent in this infinitesimal, namely by means of this type of proportion. And this is what many people sort of attempt to forget or neglect, that quantities are not so important when dealing with the infinitesimal, because the principle is that what remains, and is that what is important. And this becomes clear also along the other propositions that are following, and this is a very basic and a very important point and aspect in terms of this Proposition 18, which contributed much to Leibniz creating his beautiful notion of the calculus and his beautiful notation and the operations that go along with it, which made lives of physicists and, if you will, also mathematicians in the following history a lot easier, a lot faster, a lot more efficient. And this was actually what was the main point of Leibniz's whole thinking, that all these scientific works, they're not just there to be scientifically beautiful and to inspire a few minds capable of grasping them. No, they should be put to real use, should be put into practice, should be put into engineering, should be put into some other scientific areas and fields to make use of it for the purpose of the improvement of mankind, to make them apply actually for some things that be good for mankind, to make lives for human beings better. And this was also a big part of this notion, and basically the discovery or the development of the calculus is a real expression of this kind of attitude that Leibniz had. And when you compare this particular attitude to Newton, also in particular with this development of calculus notation that Newton may have come up with, you see that Leibniz was publishing it, he was very open about it, and when you follow his works, you see sort of step by step, very meticulously and very rigorously explained and displayed how he got to the notation of the calculus, which is not the case with Newton. So when you read Newton's works, you will find it very difficult to actually get kind of a red trail which leads you logically through the work. It's very fuzzy, it's very kind of, almost dubious in my point of view, as if he wanted to try to hide something. And this is also a difference between Leibniz and Newton. Leibniz made it as clear as possible to be put forward for practical use in real life, and while the principles of that Newton may have used there is very dubious, and for some reason he was not publishing it. He claimed he was not publishing his version of the calculus. Why actually? Because he didn't think it was important, because he didn't think it was worth putting forward for improving mankind. So all this dubiosity that is taking place on Newton's side actually contributes to the idea that actually the controversy with regards to the calculus between Leibniz and Newton was not so much about about who invented it first or something, but it was actually a political attack against Leibniz, and this whole dubiosity and this whole secrecy that was made about Newton's calculus and all these inconsistencies of he published it later and then some other work appeared from him, it is contributing to this very idea that it was not the actual calculus that was subject matter here, but it was to prevent Leibniz from becoming influential in England. And when you also read the history of not only Leibniz's mathematical works, but also his political involvements in many fields, and the history of his employer at the time, the House of Hanover, and that they were actually followers to the throne of England, and that there was a potential that Leibniz would have become a very influential person actually in England if Sophie of Hanover would have become the Queen of England. I think the Leibniz-Newton controversy was used just as a political attack to prevent this influence from Leibniz taking place in England. But more to that later on. We're going to continue with Proposition 19 in the next step, and I hope you see you around for that one soon. Thank you very much. One notion to forget. In connection with Proposition 18, Leibniz also did a scholium. Maybe we can read it a bit. It's not fully displayed here, but I'm going to read it. Word by word. I think it's worthwhile doing so. So this, if I am not mistaken, new proposition I thought to be worth mentioning, partly because of the generality of its usefulness, as it is assembling itself on all single-term analytic curves, so meaning the paraboloids and the hyperboloids, in the same way. Who therefore keeps it in mind, and it is able to use it immediately to obtain the quadrature square of such a given figure by a calculus where needed. Now it shall suffice to explain the present proposition by examples, which becomes clear by the following sentences. The curve of figure 1 shall be a cone section parabola. It is a meanwhile established fact that the squares of the distances BC, or the powers whose exponent is 2, behave like the AB or GC, or their powers with the exponent 1. Ergo, the zone C1, B1, B2, C2, C1 will behave to the zone C1, G1, G2, C2, C1 like 2 to 1. And this is just what we exercised. Okay, I'll stop right here. This Scholium document, if you will be available on the website for you to read. And he also, with connection to Proposition 18, published a corollary, which is the same document. Okay, all right. So this is all for now, and I hope to see you soon again for the next proposition. Thank you very much, and bye-bye.